Okay, please welcome a very close personal stranger, Robert Prinz, Fuzzy Logic for the control of advanced mobility support devices.
Hi everybody. Basically this is my master's thesis talk. I just gave this to a conference in Vancouver that researches biomedical technologies. So a standard mobility device is basically a cane, walker, wheelchair, or a set of leg braces. And mostly I'm going to focus on the leg braces. I've worked with Queen Alexandra and some of the clinicians there. It's a local facility that works mostly with children and the elderly to provide prosthetics and orthotics to them. So basically there's an emergence of these kind of smart walkers, so these walking systems that analyze kind of how you're moving and make suggestions. But I'm actually mostly going to focus just on the evolution of the leg brace and kind of the advanced version of it that's coming out. So basically there's an advancement in sensor technologies, actuator technologies, microelectronics, batteries, and it's led over the past 15 or 20 years, and it's made possible advanced mobility support devices that weren't practical before these technologies were released. So they're basically a powered exoskeleton of sorts that actively contributes mechanical energy to the wearer. And so if you bring up a picture of the how. It's like a passive kind of leg brace system. It gives you support in all the right places. It provides rigidity and support and restricts undesired movements. But it also has electric motors in it that actively provide movement, mechanical energy systems to the wearer. So you can program it to help you get up out of a chair or to walk. And there's also the Reebok systems. You can bring up that picture. So that's in Japan. That's the help. It was originally designed for the elderly population in Japan. They've tested it with a few clients. And this one just came out of Argo Technologies in Israel, and it's called the Reebok. And it's mostly designed for paraplegics, so people who've never left their wheelchair before are able to actually come into walking now. They use these. They have to have good upper body support to be able to stabilize themselves while using the system. And again, it's electric motors. So the same technologies that made the HAL possible also made the Reebok possible. So we're not exactly talking about the Iron Man suit here. We haven't advanced it quite to that point. It's not exactly natural. They're still relatively crude. But the technology is very much in its infancy, so we can expect to see a lot more advancements in this area. So the reason I'm knowledgeable about this topic is because an elderly gentleman from Mill Bay sent a project request to my organization on campus. That's CanAssist, and we build basically technology solutions for people with disabilities and special needs. And so it became my master's thesis topic once we met with Sid, and Nigel asked me, as the director of CanAssist, to see what I could come up with for a thesis topic. And it's a pretty ambitious project, building these systems. You can see that really I've only mentioned two groups here that have been kind of successful. There's lots of other ones that have been developed. They haven't really gone anywhere. So it turns out that assisting individuals with a powered exoskeleton is a really hard problem. I don't know, Tony Stark made it look pretty easy. So, but the complication really arises in the control system. Like the hardware's been developed, and it's simple in its concept to use motors to actually kind of help you toward your own musculoskeletal system. But so basically, the control system is really where you bog down. And so I started looking at forms of artificial intelligence that might kind of help us with this technology. Ones that are specific that can be applied to controlling human movement. And I came across an article from a professor and neuroscientist at the University of Alberta named Arthur Projeska, and he's an advocate for fuzzy logic because he says it provides a meaningful and biologically compatible way of describing motor behavior in animals. I'm halfway done. I mean, I've got the hardware already exists. We've identified a form of artificial intelligence that naturally accommodates motor control of animals, and that fuzzy logic control can be used to control electric motors. So it seems like it's really coming together for me. But what is fuzzy logic? So it's a form of artificial intelligence that's used in the autofocus of digital cameras, the control of elevators, temperature chambers, smart washing machines. In fact, the word fuzzy is associated with the word smart in Japan. They're really big proponents of this technology. Basically it's a very cost-effective way of automating complex control tasks without the need for a detailed math model. And that's very appealing to industry when you want to build something quickly and cost-effectively. So it usually relies on expert knowledge of some kind of control process. It doesn't matter if you're controlling an elevator or an exoskeleton, but it relies less on a detailed math model and more on expert knowledge of the process. So when I talk about expert knowledge when it relates to my stuff, it's mostly knowledge from physiotherapists, kinesiologists about what is good and proper movement. And you want to try and program that into an exoskeleton. So basically, fuzzy logic was originally introduced as a means of modeling natural language. So mostly kind of more from the computer science end. But its most successful application so far has been the fuzzy logic controller. As I mentioned, it's turning up into quite a few consumer products, even though you're not aware of how they work. So how does fuzzy logic work, though? What is it at its fundamental level? And basically, it's a multi-valued logic system that extends conventional set theory to include the notion of partial set membership. Now that's very academic, I know. So basically, instead of saying that any element belongs to a set or it doesn't, like normal set theory, so very Boolean logic, 0 or 1, it says that you can have partial set membership. It can be a little bit in this set and some of that in that set. And so it doesn't really go very well with North American logic convention, but the Japanese embraced it quite readily. So that's why it's very popular there. So basically, I'll give you a quick example. The element that is Chris Constable's height may have partial membership, that is, membership to some degree in the set of heights characterized as tall. And he'll likely also have partial membership in the set of heights characterized as short. Sorry, Chris. But it provides a good example. You could say, someone at 6 feet and up is 100% certain that person is characterized as tall, and below that there's kind of this gray area, or fuzzy area, right? So hence the term fuzzy logic. And that's how it works. That is the central concept behind all these control systems in our electronics today. But how is this useful other than just making fun of Chris? Basically, fuzzy logic allows us to store expert knowledge into a control process in the form of if-then rules. So if I'm falling over, then do something, take some action to prevent this from happening. So it gives us the ability to solve complex control problems without a detailed math model. And I really like that. Now, I made the mistake once of telling my supervisor, well, it helps us avoid math models, and you never tell an engineering prof that you're trying to avoid math. It's like, if there's a good math solution, do it. If there's not, then look at something else. So I really just didn't word it very well. But when you're dealing with control problems as complex as human movement, but there's a lot of knowledge about how we move, then that becomes a very kind of attractive control methodology. So, for example, if there was an anvil falling at Chris's head, and I'm standing next to him, I don't need to say, hey Chris, there's an anvil falling at your head at 3.2 meters per second, accelerating at 9.1 meters per second squared. What I need to convey to him is, look out! That's essentially what fuzzy logic was helping me to accomplish here. You don't necessarily need a highly optimized mathematical solution to every problem. It's not always necessary, but you may have some idea of what it is you want to do, and then be able to put this into this kind of rule base that you construct in the fuzzy controller. So my point is that my main focus here is human movement control and stability. And we're not looking for the perfect solution, but we're looking for a very good one. And human movement is kind of naturally efficient, so we don't need a detailed math model. We just need to know how we move and how we want to program this thing. So we just want to mimic what's already known by kinesiologists and biomechanics, or biomechanists. So what I was able to do was artificially reproduce the sit-to-stand movement. It looks relatively realistic, and I can show you to the joint plots of this, but we'll fire up the stability controller first. So I use a simple biomechanical model to simulate bringing a system into a point of stability. So we're not trying to stand up at this point, you're just trying to get from the chair to the most stable configuration. So everything in my controller is emphasized for stability, because the last thing you want to do is a robotic exoskeleton fall over. I mean, the technology is dead if someone gets injured by using it. So you have to do everything with a major focus on stability and balance before optimization for energy efficiency or anything like that. And then we'll run the second one. So the second one actually combines the stability controller with the goal controller, which then gets us up to the standing configuration. I apologize for the video quality. For some reason, it looks very poor on this player. So basically, it works quite well. I've got a bunch of other videos that show how you can perturb the system. You can push it, and it'll recover and balance. Basically, it was very well received at the conference. I had some postdocs at Toronto Rehab come up to me and tell me this is a good solution. This is the right approach. So that's my master's thesis, and I'll be defending that in a month's time.
At lunch.
I hope it stands up well.